In this series, we explore competing models for what happened at or even before the Big Bang. And two of our most popular films have been on Roger Penrose's conformal cyclic cosmology and the Gott Li self-creating universe. In this film, we'll look at a new model known as periodic time cosmology, which fuses elements of both, allowing the universe to both cycle through endless eons and travel back in time to give birth to itself.
I got into science by thinking about becoming an astronaut, thinking of going into space. I collected all sorts of stories and stats about astronauts going into space. Somehow, over time, I realized maybe that was not going to happen for me, so I started just studying the stars and constellations, amateur astronomy. And over time, I got more into the physics of what's going on. And long story short, I became an astrophysicist.
As far back as I can remember, I've been interested in time and time travel. I named my dog Kronos after the Greek god of time.
I think science really starts from fiction, basically how far we can imagine. Of course, not every science fiction will become science, but that's where imagination starts.
Since I was young, I've just felt uncomfortable within American culture. I used to look at different times instead of different places because you have all these fantasy stories and they're set in a pseudo-medieval setting that's not accurate to medieval standards at all. But, you know, as a child, you kind of get pulled into this, and when you have this discomfort, you bring it as a sort of escape.
My favorite time travel story was the comedy About Time, but more recently I watched Predestination, which is amazing because this is probably the most accurate time travel story I've ever seen.
Contemplating time travel into the past is not merely the domain of science fiction. Developments in 20th century physics show that it might just be possible.
1959, Einstein came up with general theory of relativity, and that allowed for a space-time to bend.
This bending of space-time by a massive body is what we feel as gravity. But there are solutions to Einstein's equations that show that space-time, under extreme conditions, could curl up on itself to form a loop, creating what physicists call closed time-like curves. If you could travel on this loop, you could revisit your own past, opening the door for effects to become their own causes and the universe creating itself.
The idea of the universe creating itself has this sense of, it sounds crazy, it has a lot of resistance as well, because we're used to things functioning in linear time.
When I arrived at Princeton as a graduate student, I was interested to learn about astrophysics, but my background was theory, basically theoretical physics. I had learned general relativity, and there was one person there who taught general relativity. His name was Richard Gott. One of my classmates happened to do a project with him on time travel, how you could actually have fast cosmic strings going past each other, and they may enable time travel. I mean, that was kind of exotic. That wasn't quite what I was after. I knew general relativity, so I worked with him at least as a teaching instructor. He was a very interesting character. Whenever I stepped in his office, it would take 2 hours to get out. It wasn't very easy to extract yourself. In fact, I had forgotten that, but I talked to him more recently, and it was the same thing, basically. You couldn't talk with him for less than 2 hours. Li was a more senior graduate student in astrophysics. So in fact, I overlapped with him for about a year. So he's now a senior professor in Beijing.
Together, Gott and Li battled Stephen Hawking, who conjectured that time travel to the past was impossible. They argue that not only was Hawking wrong, but if we trace the history of a rapidly expanding or inflationary multiverse, we will find at the root of its branching structure an era of closed time-like curves.
The great thing about inflation is that a little tiny inflating piece grows up to be an enormous inflating piece, each little bit of which is exactly like the little bit that it started with. So what if one of those little bits was actually the bit that it started with? Then it could give birth to itself. Something funny had to happen at the beginning of the universe, and time travel and solutions in general relativity seem supremely suited for the purpose.
It's quite an entertaining paper that they wrote, and in fact they wrote it around the time that I arrived there, maybe shortly before I arrived. They came up with a scenario that looked reasonably consistent and at least consistent with certain laws of physics as we understand it. The main, I think, weakness with Gott Li's model, even though it's very imaginative, is there's really no way to test it, or there is no smoking gun to say, okay, so this tells me that time travel might have happened in the early universe. Now, that being said, you may also think that quantum mechanics is strange, and if you believe quantum mechanics, something like this must have happened in the early times. And that's kind of the realm of quantum gravity. So maybe in the future, when we understand the interaction of quantum mechanics and gravity well enough, then we convinced that something like this must have happened, even though we cannot directly test it. Beth Gould was my PhD student. She was interested mostly on foundations of quantum mechanics. I was interested in cosmology, so we tried to find a common ground there. She mostly worked on testing models of cosmology. In particular, she worked on holographic cosmology, which is a model we worked on before periodic time. But then I asked her, okay, so what are you interested to do next? And she really wanted to get to the question of causality in quantum mechanics. And in fact, there is something weird in quantum mechanics, that the cause and effect don't seem to quite make sense if you go to the quantum world. So so you could think about like these virtual particles that come in and out of vacuum in quantum mechanics. In fact, that's responsible for Hawking radiation, things that just pop in and out of vacuum. You can just think about them as particles going back in time, something that, in fact, loops of particle that kind of go forward in time, turn around, and go backward in time. And they cannot happen classically, but according to quantum mechanics, these things could happen because essentially anything that can happen will happen, and over short time scales, everything can happen. On larger scales, it would be exponentially unlikely. But that kind of gives you the idea that this idea of causality, that there is always a cause that precedes an effect, might just be an illusion, like a classical illusion, the same way that we think about positions of particles and velocities of particles to be something fundamental. And in quantum mechanics, we know that's not the case. You cannot measure the position and momentum at the same time, for example. Maybe the whole cause and effect thing, that there's always a cause that precedes an effect, is not really fundamental. It's just something that appears to us as classical observers.
Inspired by what had come before, Ashforty and Gould wondered if a different type of time travel mode was possible. Instead of a closed time-like curve at the origin of time, as in the Gott Li model, the entire universe, like Bill Murray in Groundhog Day, might be trapped in a closed time-like curve. They called this periodic time cosmology.
Through trying to figure out what literature there was on some of these closed time-like curves and or retrocausal quantum mechanics and other interesting cosmology. And one of the questions I had is whether or not anyone had ever looked at this possibility of having the universe come back around like this. And so when I was developing it, I was saying, well, if I can't find anything that's ruling it out, well, maybe I should see if I can put something together and see if, well, I figure out if it's plausible or ruled out.
Beth was thinking about this idea of retrocausality, which is maybe in quantum mechanics, future measurements could impact past decisions by experimenters. Which is a very weird notion, but it's one way of understanding some of the surprising results of quantum mechanics, that somehow future can impact the past. So that's where I thought, okay, so how can we push this to the extreme? We know our universe is, we know we don't see obvious violations of causality around us, but our universe is big, and on very large scales, weird things could happen. Our future is uncertain, our past is uncertain. And quantum mechanics, even though we usually think of it on a small scales, gravity could actually couple larger scales to smaller scales. And this is kind of one of the things that gravity does. Gravity doesn't have a scale. And the very big things and very small things happen to, in fact, in the string theory, there is even a duality that maps very big things to very small things. It's called T-duality. So this is one of the things that gravity does, that if you want to have quantum mechanics and gravity, you have to kind of really get rid of the notion of that their separation of the scales. So kind of these things going around in our head, and at the same time, Beth started reading Roger Penrose's book that came out on conformal cyclic cosmology. So those were kind of the ingredients that all kind of lined up around the same time, that maybe we could just rethink causality on the cosmological scales.
You have the Big Bang, you have a beginning of time. And you ask, well, where does that come from? There is sort of this unsatisfactory, well, what came before that and what came before that? And so one method of getting around this, what came before, is by having this loop within the model.
Ashforty and Gould wanted a self-contained model of the universe where the future can join to the past. But the universe is expanding and cooling, whereas the Big Bang was hot and dense.
We need a way to close this story, and fortunately around the time, Roger Penrose, who is this giant figure in relativity, who just won the Nobel Prize a couple of years ago for his contributions to the discovery of black holes and theoretical understanding of black holes. So he came up with this idea that maybe a universe could suddenly change size because the sizes become meaningless at very early times and very late times.
But what if, at some fundamental level, size does not matter? Mathematicians call this conformal geometry, where only angles matter and distances do not. So, for example, a big and a small triangle are the same in conformal geometry, so far as they have the same angles. This conformal geometry is the basis of Penrose CCC, conformal cyclic cosmology, which allows for our dense, fiery past and dilute, cold future to be the same. This titanic change in size is known as conformal rescaling.
Einstein tells you that mass and energy are equivalent. Planck tells us that energy and frequency are equivalent. That tells you that mass and frequency are equivalent through these two very basic laws. That basically tells you that any stable particle which has a mass, massive particle, is a clock. So if you want to measure geometry, you use clocks. Okay, you have good clocks if you have mass, but if you don't have mass, you don't have good clocks. And there are two places where it can be argued you don't have mass. One of them is in the Big Bang. So you go back and back in time and you get to the Big Bang. Now the thing is that the Big Bang is extremely hot, means that particles are racing around at a great speed. When you get nearer and nearer to the Big Bang, you find this speed is so enormous that the masses of the particles are completely irrelevant.
Once all matter in the universe is swallowed by black holes and the particles lose their mass, which is one of the assumptions, controversial assumptions of the CCC model, there are no massive particles left and no physical clocks. And what Roger argues then, it only the conformal geometry which matters.
So this is known as conformal cyclic cosmology. And the name conformal means that at some point the scale loses its meaning. Of course, that's not the case now. Right now we understand what's big and what's small, but there is this general tendency in physics that fundamental theories must not have a fundamental scale in them. And Roger kind of pushed this to its extreme, saying that at the infinite future and infinite past, in fact, that happens. So all the scales disappear, and then you could have a very big universe that matches a very small universe.
The conception at that point is you can then rescale the universe at those boundaries where you don't have mass anymore, where you don't have a preferred scale. And when you do that, you're capable of then matching this scale invariant end of the universe to the scale invariant beginning of the universe. So for Penrose's model, you have this series of eons. Basically, it's a bunch of universes stacked one on top of each other. Everyone starts in conformally invariant and ends conformally invariant. And so once you get to the conformally invariant stage, you resize and restart to a new universe. Within periodic time cosmology, instead you're matching this end to the beginning. So it's a big loop instead of this ladder of eons.
Really, the only way that a very big universe can match a very small universe is if really there is no scale, because they are very different, a very big universe and a very small universe. So that's, I mean, mathematically, that's the only thing that really makes sense. A very big and very small, if they could be the same thing, there shouldn't be any scale. Incidentally, that's how a universe looks like. So if you look at the structure of a universe on very large scales, and you should look at the cosmic microwave background, and you have to be very clever to actually understand what that means, because if you look at cosmic microwave background, there are all sorts of structures on it. There are sound waves, acoustic structures that are now mapped very well with the Planck satellite and other cosmic microwave background maps. But if you could back out of those maps, those exquisite maps, if you can back out what was before, what was the initial conditions, you actually find something as very featureless, almost perfectly scale invariant. And that is something that lends itself perfectly to conformal rescaling or to conformal symmetry, because if something doesn't have any preferred scale, then if you shrink it or expand it, it will look the same. And that's kind of why this idea of conformal rescaling or conformal cyclic cosmology a la Penrose is in fact a perfect match to how a universe looks like. And I'm kind of sorry that I don't think Penrose doesn't appreciate that himself. In fact, I think that's the strongest argument for conformal symmetry of a universe, because it looks a scale invariant on larger scales. So these are match made in heaven. Penrose's model of conformal cyclic cosmology had some radical assumptions. So he wanted the mass to disappear at early times and late times, which is basically the assumption of conformal universe at very early times and late times. And he wants all the information to be destroyed when they fall into the black holes. Whether we need all of them or not, I think the answer is kind of mixed. We really focus on matching observations, and what happens at the fundamental level, it's a little bit harder to answer. So we certainly rely on assumption of a scale invariance, which basically universe must be conformal at early and late times. So there shouldn't be any mass, because then you cannot rescale the universe. If there's a fundamental mass, there's no way to rescale it and end up with the same thing. So that we should certainly assume. But what happens to black holes and what happens to information is a little bit of a tricky question, because in an infinite universe, information, well, you have infinite amount of information. So whether it disappears or it just scrambled all over the place, we don't really know. And that's a harder question to answer.
Since both CCC and periodic time cosmology utilize conformal rescaling, what is the advantage of invoking a closed time loop?
One of the interesting things about having it exactly periodic is it creates a constraint. So it means that there are more limits on what you can get, on what your model looks like. What if we take the constraint that what we have at the end of the universe has to be what we have at the beginning, and see what that does?
So these are bizarre ideas. If universe repeats itself, but can it be tested? And that's something that we kind of obsessed over for some time. But it seemed that it's possible. So we have this, in particular, this consistency that we want a universe which is a scale invariant on larger scales, because there is no preferred scale. But of course, we know right now there are scales in the universe. There are galaxies, there are stars. So these scales emerge somehow, and that changed the scale invariance of the universe. Right now, the universe is not a scale invariant. But then at the end, we want to reset everything. So something must happen to rescale all of this, and that was kind of the assumption. The simplest thing is some sort of overall rescaling. That's what Penrose, in fact, suggested, the conformal rescaling. And then everything should look the same. And Penrose thought overall everything should look the same, and we proposed that in detail everything should look the same.
Ultimately, the judge of any scientific theory must be empirical data. And ideally, a model of the early universe should make predictions for the patterns of variation seen at 1 part in 100,000 in the cosmic microwave background. The properties of these patterns are often measured using something known as the power spectrum, essentially counting the strength of blips of different sizes that you see in the sky.
Periodic time model is based off of this restraint that the power spectrum you get out at the end of the universe becomes the power spectrum coming back in, although it might be rescaled at a different scale. So you're taking what you get out at the end and you're putting it back in as that input parameter.
So that gives a prediction for a spectrum of fluctuations on various scales. So it turns out that the scale invariance on very large scales, it's what you expect, but then the subsequent evolution destroys a scale invariance on the smaller scales. So that's a very characteristic prediction, which in fact ties our evolution of our universe today and in the past and into the future to the initial conditions of the universe, because our past is our future. And this is a unique and bizarre kind of self-consistency, because you want the evolution of the universe, dynamics of the universe, what's happening this very moment, the fact that there is a dark energy, that it might be evolving, it may not be evolving. It actually tells you what happens when the next time the universe restarts, which is in fact our future, our past, so it's going to be our past. So our initial conditions, how our universe started, depends on what's happening now and what's going to happen into the future. And we have a theory of what's happening now, what's happening into the future. We have the cold dark matter, we have dark energy, that seems to fit data very well. And we can use that to see what is a self-consistent scenario. And we can now test that and look at the structure in Planck data, Planck cosmic microwave background fluctuations, and other cosmological observations.
So the big question is, does periodic time cosmology fit the data?
It's not as good of a fit as the typical power invariant spectrum to the Planck data, but it's still within the threshold that we would typically consider in physics to be potentially viable.
It turns out the model is not quite as good a fit as the standard model. If dark energy, the substance responsible for the universe's accelerated expansion, is a constant. But what if it changed over time, ever so slightly?
So if dark energy evolves a tiny, tiny bit, like a few percent every few billion years, then that's enough to actually make our evolution consistent with our initial conditions, which is, I find it really mind-boggling, because it really ties our future to our past in a very, very concrete and quantitative way. So we predict then that dark energy should be getting ever so slightly bigger over time, only a few percent every few billion years. And that's a prediction, so that's something that cannot be tested right now because our experiments aren't quite there yet, but maybe in 10 or 20 years we could actually measure the evolution of dark energy precisely enough to see whether that's actually the case.
By studying the light of ancient galaxies, future space telescopes such as ESA's Euclid mission and NASA's Nancy Grace Roman telescope, as well as ground-based telescopes like the Vera Rubin Observatory, should be able to more accurately probe the history of dark energy over time.
So a combination of all of these surveys will be able to tell us much more precisely whether dark energy is evolving, and if so, how much. And hopefully then this prediction can be tested in the near future, if not 10 years, maybe in the next couple of decades.
One of the things you have is that you have this exact periodicity, and when you match it, you get the rescaling that you have, like every time you stretch it. And you get what that exact is. So you'd expect a repetition in the power spectrum on that scale. You'd be able to observe the exact periodicity in principle. So that would be something that you would expect to see from this that you would not expect to see if you don't have the exact periodicity, because you'd have a different universe coming into this universe, or an inflationary stage, and so it'd be more random. You'd have to look at what exactly those artifacts are and figure out which ones to find.
Cosmic inflation is the hypothesis that the universe underwent a brief but incredibly rapid rate of expansion. But like CCC, periodic time cosmology alleges there was no inflation. So if it's to have any chance of success, it must address the cosmological puzzles that inflation is thought to solve. The first is known as the monopole problem, and was inspired by grand unified theories of physics that were being explored in the 1970s. These theories implied the universe should be flooded with strange particles with only one pole, unlike normal magnets, which are always dipoles. But these monopoles are not seen in the universe today. Inflation solves this by its rapid stretching, diluting the number of monopoles to practically zero.
The idea is that the grand unified theories should give you a lot of monopoles if the universe was hot enough, and they would overclose the universe. The universe wouldn't be as big as it is today if you produce all those monopoles. Now, we don't really have grand unified theories, so that was 30, 40 years ago, and even until now, we haven't actually found these grand unified theories, so we don't really know if that's the case, that these monopoles exist. If they exist, are they stable, and so on. So it's not clear that it is a problem. Certainly something that can be solved by inflation, had this been a problem. And it could be a problem for us, but we don't really know if the monopoles are there.
Another puzzle is, why are the CMB photons all roughly the same temperature when there hasn't been enough time since the Big Bang for them to be in causal contact? Inflation resolves this horizon problem because the patch of space that our universe expanded from was much smaller before inflation than in other cosmological scenarios.
In our particular model, I mean, the space that you have, that we see is causally connected, was causally connected before, since it was causally connected now. With periodic time cosmology, like all the bounce models and such, you have more time, basically infinite time, for things to thermalize.
A further issue is known as the flatness problem. This was discovered by Bob Dickey, who pointed out that a flat universe is inherently unstable, and so we should expect to see the universe to be curved, yet we don't.
Inflation can actually expand the universe by many, many orders of magnitude, so no matter how curved it is, after inflation is done, it could look very, very flat. Now, then that goes back to the question of what do you think is a natural initial state of the universe? What I described to you as a conformally invariant initial state doesn't have a scale. Then within basically the set of a theory, there cannot be a curved universe. The universe cannot have a scale in it. And in some sense, so that problem of flatness is solved by assumption. Now, it's not clear whether it is a solution or it's an assumption. One may argue about that. But it's clear that if you assume there is no scale in the universe, it cannot be a curvature scale.
A key difficulty for any cosmological model is to generate a scale invariant spectrum of fluctuations in the CMB, which will eventually seed the inhomogeneities in the universe to generate the structure of galaxies that we see today.
A uniform universe certainly looks the same if you rescale it. And if it's a very non-uniform, then it violates this assumption. So in some sense, you could say that a scale invariance, or this conformal symmetry at early and late times, is the ingredient for solving the most pressing problems with a standard cosmology, which is solved in a very different way than inflation.
Inflation isn't really proven, it just was the only model that survived. But since then, we've had other models that also fit this, and inflation isn't really a single model. There are many models of inflation, and you can construct it for many different, to match the data however you want. So it isn't actually as secure as people might think. So speculating of alternatives is not necessarily that much of a bad thing. And, I'm not here to say, oh, my model is the solution to everything and it's so much better than everything else. It's not. I think it's worth exploring the possibility, and I personally think it's wrong to just ignore it.
It's often thought that one way to distinguish between inflation and alternatives is to probe for ripples in the fabric of space-time, known as gravitational waves, not coming from black hole or neutron star mergers, but from the Big Bang itself. Inflation produces these, whereas many rival theories do not. So what about periodic time cosmology?
That's something that we don't actually have a prediction for because, in fact, we cannot predict the amplitude of things that come out. We can only predict the shape of them. So if there were no gravitational waves, that's consistent. There will remain no gravitational waves. Now, there have been gravitational waves created by astrophysical events. So they are there. We already detected them with LIGO, and they will be detected better with future gravitational wave detectors. They could survive from previous eons on small scales because one thing that as I described, this model does is kind of shrinks the structure from previous eons to small scales. So they would be there, but they would be on very small scales. It would be hard to detect them, harder than they are now, in fact. Yeah, they are pretty hard now.
It's been alleged the cyclic models are in conflict with the second law of thermodynamics, which states that entropy, roughly a measure of disorder, almost always increases over time. If there had been an infinite amount of time in the past, then why don't we have a maximal state of disorder?
We can overcome this difficulty by saying that you have an infinite universe. So if you had a finite universe, then in fact there was a finite amount of information, so your disorder could increase. But if you have an infinite universe, you have this infinite sea of information basically, and if you basically keep getting new material from larger scales, new information, and the old ones, they all go to very, very small scales. What happens to them, we don't know. If you have a conformal universe, in some sense, there must be infinite amount of information because you can kind of keep scaling things, and there is no minimum size because there is no absolute size. So that's the way we get around it. The infinity is bigger than infinity and smaller than infinity. So entropy can keep increasing and still be infinite.
Another problem for time travel is that it seems to lead to paradoxes. For example, in Back to the Future, Marty McFly endangered his own existence by preventing his parents from falling in love. But if he was never born, then he couldn't travel back in time to prevent his parents from falling in love.
In your typical time travel story, like for instance Back to the Future, you go back in the past and then you affect, in that particular story, your parents' meeting, and that makes you no longer exist. This would not really be possible in this particular model because it's not human. It's not human scale. So basically, you have to travel all the way to the end of the universe, and because of how the end of the universe is defined, you'd have to no longer exist as matter before you get back to the beginning of the universe again, in which case you have to go through the extremely hot early universe in which matter doesn't exist as it does in the current universe before you get back to our world again.
Nevertheless, one can still ask, what does causality mean if time travel into the past is possible?
The thing about causes and effects is that it's not something that you really need to do science. It's kind of part of the story. And what you really need to do science is you want to make predictions that can be tested. And as long as you have a predictive framework for that, then you can do science. Right? Now, whether there have been causes and effects, that's kind of a framework that you want to fit your stories in. but maybe universe doesn't want to fit into that story. And certainly periodic time cosmology doesn't fit into that story.
You might have the whole closed time-like curve, and at that level, causality is kind of not an appropriate concept. But if you focus on individual segments of the curve, you might have unidirectional cause and effect just restricted to that particular segment. And so we're right to think in terms of causality at the local level. When we zoom out, causality as such ceases to apply, but we can still do physics.
Traditionally, we think of only religion as promising an afterlife. But if history exactly repeats itself, as it does in periodic time cosmology, does that mean we will get another life?
In our scenario, which is self-consistent across cycles, there are infinitely many versions of you that exist in the universe on various scales. Some of them are very tiny, some of them are very big. Whether you can communicate with them is not clear. You may or may not. Probably it's going to be hard to communicate based on current observations with them. They're going to be outside your cosmological horizon. That would be actually another exciting possibility, that if we could get signs of kind of in different versions of us existing, or at least structures existing in different parts of the universe. So basically the idea would be that the same structure that you see, a more primitive version of it would be like 100 times bigger somewhere else in the universe, or 100 times smaller somewhere else in the universe. Unfortunately, those somewhere else's may be outside our cosmological horizon, so we may not be able to actually directly see it. So we may just infer them statistically, which is what we did with Beth, in fact. But actual structures should exist somewhere in the universe that match each other. And that's kind of the way that cycles work, is that no individual observer goes to itself, but these are infinitely many versions of us spread across the universe. And then one of them kind of matches to the other one as time passes. Kind of the information that built you would be spread in different places. And I guess this is the thing, like when you die, what happens to your information, right? So it's not necessarily your particles, because your particles might be, when we die, our particles might be buried in a coffin, but our information might be still spread across the universe. You are emerging for a century or so in kind of something that's localized, but your information was much more spread before and will be much more spread afterwards. And it's going to be the same thing in the periodic time cosmology. Except that basically the same thing kind of goes in cycles. So you have infinitely many of these happening at the same time.
I personally wouldn't say that people are more. I'd say it's just the same instance. But I have a different way of looking at things than I think that other people do. So I think I'd leave such considerations to how people want to think about life and death.
The ancient Greek philosophers, especially the Stoics, speculated that the history of the universe endlessly repeated itself, an idea reinvigorated by Nietzsche in what has become known as the eternal return hypothesis. So does periodic time cosmology follow this tradition?
I think he had in mind basically us in the exact same form. And our proposal, our picture, which in fact is not just an imagination, it's something that can be tested, and we have tested it very concretely, is that could happen for the universe, but for you in particular, it wouldn't be exactly the same. So there are infinitely many versions of you spread across space in very different forms. Some of them are very primitive, some of them are much more evolved, and basically what happens that every time you go through the cycle of time, which takes infinitely many years, one of those versions maps to another version, and so on. So in some sense, there are infinitely many of you already in existence. You may not remember them, but they are there, but they are in very different forms.
In the extreme conditions of the Big Bang, physicists believe that Einstein's theory of gravity, general relativity, and quantum mechanics should be united in a quantum theory of gravity. So ideally, any model of the Big Bang should be tied to such a theory.
That's another way to motivate this, because of course there are a lot of people who are interested in quantum gravity and what could and could not be consistent. For example, in the string theory, There are dualities in string theories that map very big and very small to each other. So could that actually be something that is realized in this scenario? So those are kind of directions that may be explored, but at some level it's at the whims of, I guess, the academic community and funding agencies. And what else happens? Will there be something more exciting that happens? I have other models that I work on, and I have other predictions. If they come true, then probably I would spend more time on them.
Periodic time cosmology is a mind-blowing proposal for the early universe that may well realize some of the oldest ideas from philosophers in a concrete scientific proposal. While it's still a work in progress, its prediction of an evolving dark energy may be tested in the coming decades, perhaps revealing if the universe created itself.